This screencast is about continuing our explorations through equilibrium, and in this case we're going to be looking specifically at buffers and the HH or Henderson-Hasslebalch equation. Alright, a buffer is any solution that contains both the weak acid and its conjugate base. So like we were looking at with the common ion effect in the previous lessons. A buffer is something that has, because it has both the acid and the conjugate base, it can resist changing pHs because it has both an acidic component and a basic component. An example is the human blood, which has, it's buffered to about a pH of 7.4. And when we're trying to introduce medicines and other components of the medical field, they have to be really cognizant of what pH the substances are, so they buffer them so that it matches what you're trying to work with. So you'll hear those kind of terms a lot whenever you're looking into medicine or you're in one of the medical fields. Because we're dealing with both the acid and the conjugate base, we saw in the ice chart that it affects the end resulting pH because the concentrations change. And so through a series of mathematical computations and a whole bunch of equations that you can derive if you wish, Henderson and Hasslebalch both developed an equation that has made our job much easier in solving these problems. And you're kind of going to wish that I had showed you this equation way back earlier because it'll make your life much easier. So the Henderson-Hasslebalch equation is shown here on the screen. It says pH equals pKa plus the log of the conjugate base concentration divided by the acid concentration. So the log is of this whole thing, okay? It's very straightforward when you're solving it and you know the conjugate base and the conjugate acid, you know, because you use the log function on the calculator, add it to the pKa, and you get your pH. Now, remember, when you have to find pKa, you're going to just do the negative log of the Ka. So that's pretty simple. The confusion, and it's not really confusion, but it makes it a little bit more challenging, is when you're asked to solve for one of these two pieces here, because you have to do the inverse log. At this point, we've done that so many times with all the different equilibrium problems we've solved for that you really should have very little issue with operating your calculator and manipulating the variables. Alright, so here is a problem. It says, what is the pH for a buffer that is 0.12 molar lactic acid, which is HC3H5O3, and 0.1 molar sodium lactate. So you can see that you have both lactic acid and you have the lactate ion. They give you the Ka for lactic acid, and if we were doing this problem in a traditional kind of way, we would set up an ice chart like you see here, and we know that we're ultimately looking for this value here. So we're going to have x's again because we're changing, and we know that this is going to be x and 0.1 minus x, no, plus x, and then on this side we're going to have 0.12 minus x. Our Ka is 1.4 times 10 to the negative fourth, and that is going to be equal to our products, 0.10 plus x over 0.12 minus x. We look at our values and we see that our x factors are tied up with a number that's to the -1 exponent, and our Ka is -4. So we're going to go ahead and make the assumption that these k's, or I'm sorry, these x's do not contribute. So we are given, we see that is 1.4 times 10 to the -4th equals x times 0.10 over 0.12. And so when you do the math and you do the algebra, you end up with your x being 1.7 times 10 to the -4th. Now, the question asked us for the pH. So the negative log of that value, our pH would give us 3.77. All right, so we are very good at doing this type of problem, and it's no big deal, and we've done them a million times. But on the next screen, we're going to look at how we can use the Henderson-Hasslebalch equation to make the steps a little bit easier. So here's the same problem again. We have the 0.12 of the lactic acid, and we have the 0.10 of the lactate ion, and our Ka is listed here. So to find the pH, we're going to do the negative log of our 1.4 times 10 to the negative fourth, and so our pKa will be 3.85. Okay, so pH equals 3.85 plus the log of our conjugate base, which is 0.1, over our acid, which is 0.12. So to solve this problem, I'm going to go ahead and do the division and take log for that value, and I get a value of negative 0.079, and I have my 3.85 that I'm going to carry down, and that whole thing is going to be my pH, and when I solve it, my pH ends up being 3.77. So you can see that this process, the Henderson-Hasslebalch equation, has greatly reduced the amount of strain on our brains and the amount of time it takes to process one of these equations. As long as you know your acid and your conjugate base, you can plug it in along with your Ka value, and you find your pH. You can be asked to find the pKa, and they might give you the pH. Any of these components can be left out, and you can easily manipulate this equation and get the resulting answer. So Henderson-Hasslebalch should be your new best friend. Make sure you know the equation for the test, because it will be used.